I wanted to pop in and give you a brief introduction to our new unit, Radicals. I know you guys have been working hard all week on this new chapter, so I wanted to pop in and just sort of give you a brief overview of the important definitions, vocabulary words, and concepts that you are going to need for this chapter in case you are having some difficulty. Hopefully this can help clear some things up. So this is my introduction to radicals. I hope you find it helpful. So what is a radical? Well, it's this handy dandy little symbol that you see right here. This is a radical, right? So whenever I use that word, that's what I'm referring to. I'm referring to literally this symbol, radical. But with the symbol comes like this entire operation, which is pretty cool. So let's talk about what does it mean to be a radical. So radicals are the inverse operation of exponents. And you guys, inverse operations are nothing new to us. If I said, what is the inverse operation of addition? You would immediately tell me subtraction. If I asked you, what's the inverse of subtraction? You would tell me addition. If I asked you, what's the inverse of multiplication? You would tell me division, right? Inverse just means it undoes. What if I said, what's the inverse of division? You would instantaneously tell me multiplication, okay? These are inverse operations. Well, the inverse of a radical is an exponent, and the inverse of an exponent is a radical. So what does that mean? It just means that radicals undo exponents and exponents undo radicals. Just like addition undoes subtraction and subtraction undoes division, radicals undo exponents and exponents undo radicals. Okay? And it might sound like a weird concept, but the more you get working with them, the more just natural and secondhand and second nature, this will become. Just like multiplication and division being inverses is just second nature to you, and subtraction and addition being inverses is just second nature. It's automatic. You just know it. It's going to feel the same with radicals and exponents the more you work with them. Also, just a quick note, it is incredibly helpful to think of an exponent as a copy maker. And what do I mean like that? What do I mean by that? So I give you some examples here, right? So 4 squared, the exponent there is 2. That means I want to multiply together 2 copies of 4. So 4 times 4, okay? So that exponent 2 is just telling me I need 2 copies of 4 multiplied together. Let's look at another one. Negative 5 to the 4th power. My exponent there is 4. That means I want to multiply together 4 copies of negative 5. So negative 5 times negative 5 times negative 5 times negative 5, right? My exponent was 4, so I'm multiplying together 4 copies. And then I have one more example here. The quantity 7x cubed. Well, here my exponent is 3, so that means I want to multiply together 3 copies of 7x. So it's 7x times 7x times 7x, right? Think of your exponent as a copy maker. Whatever number your exponent is, you want to multiply together that many copies. Okay, so start to think of exponents as copy makers and radicals as like copy taker outers. And we'll talk about that as we move forward a little bit. Okay, so now it's time for some definitions. The biggest and most important definition that I want to start you off with is we say that C is the square root of A if C squared equals A, then C equals the square root of A. And I know that that sounds confusing just to throw that definition at you. So let's look at it using an example that we know, right, guys? Always, what do I always say? Start with what you know. So we're going to start with square roots and we're going to throw some numbers in. We know square roots. We know how to work with numbers. All I'm saying is that if 4 squared equals 16, well then the square root of 16 equals 4. That's it. This, in essence, is exactly what we just talked about. Exponents and radicals, you guys, are inverse operations. One undoes the other. How do I undo this exponent? Well, I take the square root, right? I take the radical of it. All right, that's all this is saying is that they are equivalent expressions. One undoes the other. It is the same as me saying, let me put this in terms of operations we're really familiar with, addition and subtraction, right? If A plus B equals C, well, if I want to solve for A, then A must equal C minus B, right? I use this subtraction to undo the addition. And if you look at it over here, okay, I threw some numbers in to make it just extra clear. A plus 5 equals 9, and I told you to solve for A. You would automatically subtract to give you A equals 9 minus 5. Because you know, to undo this addition, we need to subtract. It's the same thing with your radicals, you guys. To undo this exponent, we need to take a radical. Okay, same thing. All I'm saying with this definition is that they are equivalent expressions. One is undoing the other, okay? And as we do more examples, that will start to sink in more and feel a bit more comfortable. So let's look at an example. Let's use this definition I just gave you to simplify something, okay? So here's the definition I just gave you right at the top. We say that C is the square root of A if C squared equals A, then C equals the square root of A, right? This radical is going to undo this exponent. That's all that definition is saying. They're equivalent expressions, one undoes the other, okay? So here's my example. I said use this definition to simplify the square root of quantity 7x squared, okay? Guys, look at this. I have, let me just grab my pen tool, sorry about that. I have a square root and an exponent. They're going to undo one another. They're canceling each other out, right? So I'm left with 7x. Now, why do I have these absolute value signs here? Well, that's because think about when you're squaring something, when you're multiplying two things together, okay? If those two things are positive, so let's say 7 times 7, 7 squared, that would give me 49, right? But there's another way I can get 49. Negative 7 times negative 7. When I square those negatives, they cancel out, and I still get that positive 49. So to take the square root of 49, well, I could have positive 7, but I could also have negative 7. Both of those answers work. When we are working with radicals, you guys, we are only concerned with what I'm going to call the principal square root, which just simply means the positive square root, okay? So we need to throw absolute values around 7x because it could have been the negative that we squared together to give us what was under our radical. So we need to throw some absolute value signs around it, which just means take the positive value, okay? And the positive value of 7 is 7. We don't know what x is. It could be a negative or a positive number. So we have to leave those absolute value signs around it because we don't know if it's negative or positive. So we need to be extra cautious and leave those absolute values around it because x is an unknown. We don't know what it is. So regardless of what it is, we're just saying we need the positive of it, okay? As we move on, those absolute values, they're going to sort of go away because our problems are going to say, just assume it's the positive it's the positive root, it's the principal root. But I just thought it was important to point that out to you. And especially if you see that notation as you work in your homework or in your book, that's what it means. It just means we want the positive principal root, okay? And let me prove this to you. So let me get rid of all this gobbledygook here. Just so makes it look a little bit nicer for you. So let me prove that this is in fact true. So we have the quantity 7x squared. Remember I said think of an exponent as a copy maker. This means we want two copies of quantity 7x multiplied together, right? 7x times 7x. 7 times 7 is 49. X times x is x squared, okay? Radicals are really nice. Remember, multiplication is like the best operation in algebra because it lets us basically do what we want. We can split the radicals up, which gives us the square root of 49 times the square root of x squared. The square root of 49 is, again, we're taking the principal square root, so 7, and the square root of x squared is just x, and we need to put those absolute value signs around it just to say we want the positive, the principal square root of that variable. Okay, so the math works out beautifully. Let's look at another one, okay? Let's just look at one more just to really drive this home, okay? So again, let's use that definition. We say that c is the square root of a if c squared equals a, then c equals the square root of a. What does that mean? It just means that exponents and radicals undo one another. C squared equals a and c equals the square root of a are equivalent expressions, right? Just like multiplication undoes division, exponents and radicals undo one another. They're inverse operations. So here my example was, use this definition to simplify quantity negative 8x squared, okay? This radical and this exponent are going to undo each other, so I'm just going to cross them out. They cancel each other out, guys, just the way multiplication and division cancel each other out. Well, radicals and exponents cancel each other out, and I know that looks very sloppy, I apologize for that, but pretend I can just erase those things, right? They cancel each other out, which leaves me with just negative 8x, but of course I'm only concerned with the principal square root, that positive square root, so I have to throw absolute value signs around it. The absolute value of 8 is 8. I don't know what x is, so just to be safe, I have to leave the absolute value signs around it in case it is a negative number, because x is unknown, okay? And again, here's my proof. All right, I have the square root of quantity negative 8x squared. Well, we have our exponent. That's our copy maker, which means we want 2 copies of negative 8x multiplied together, which is exactly what I have here. Negative 8x times negative 8x. Negative 8 times negative 8 is 64. See how that negative went away? That's why it's so important to put those absolute value signs around. X times x is x squared. Okay, again, algebra is so nice, we can just split up multiplication when we want to. Multiplication is the best operation, I say it all the time. So we can split up the square root of 64x squared into the square root of 64 times the square root of x squared. The square root of 64 is, of course, 8, and we're looking for the principal square root there, so we're going to take the positive 8. And then we need to throw the absolute value signs around the x because the square root of x squared is x, but we don't know if it's positive or negative, so we're just going to throw those absolute value signs around it just to be safe. Okay? All right. Vocabulary in this chapter is incredibly important, okay? Only because I'm going to be referring to these things in your book, is going to be referring to these things in your homework, is going to be referring to these things using very specific vocabulary and language. So let's talk about what each of these pieces are, okay? We have one piece here, we have another piece here, and we have another piece here. So let's talk about what are all of these things and what do they mean. So the first thing we're looking at here, whatever this little number is that's going to be right here inside your radical, that's called the index, okay? The index is the root you are taking. In this example, the index is n. Typically, there'll be a number there. N is just standing for numbers. So a 3, a 4, a 5, a 6. If you're taking the cube root, there'd be a little 3 there. If you're taking the 4th root, there'd be a little 4 there. If you're taking the 5th root, right, there's going to be a little 5 here. It's whatever this number is called the index, and that's just the root that we are taking. Okay, that's all that means. I do want to note here, though, that when taking square roots, the index is an invisible 2, right? You guys, if I just said square root of 16, there's no little 2 here. That's because square roots are the most common roots we talk about in our algebra class, and they're so common and we talk about them so much that we don't even denote that index anymore, okay? So if you don't see a number there, it just means square root of 16, right? We know that. You wouldn't even think about it. If you saw this written on your paper in your book, you would just think, oh, okay, square root of 16. But it's worth noting that there is an invisible 2 there. The index of that radical is 2. Okay. The next thing we're going to talk about is the radical, and that's literally just this symbol. Okay. So when you hear radical, that's literally just the symbol we're talking about. It's just this right here. Okay. The radical. All right. And then, of course, the last thing is the radicand. The radicand is whatever is under the radical, okay? So it's whatever you see inside here, okay? So in this example, the radicand is xy. It's whatever you're taking the root of, okay? In that example I used before, the radicand would be 16. It's whatever number or variable or whatever is underneath your radical, okay? That we refer to as the radicand. So you've got the index, the radical, and the radicand. 3 really important words. Of these, I'd say the most important new word you're going to be using all the time is index. I'm going to constantly be referring to the index, okay? So that's really important. So let's just quickly look at these vocabulary words just to make sure we're really comfortable with them, because after this I'm going to do a lesson where I use those vocabulary words a lot. So if we look at this example right here, let's think, what's the radical, what's the index, and what's the radicand? So in this example, the index is 3, right? This is a cube root. The radicand would be 24. That's what's underneath my radical. And then, of course, the radical is just the radical symbol. So in English, if I saw this on my paper, I would say the cube root of 24. So we read this entire expression as the cube root of 24. Let's look at one more example. And again, I just wanted you to be really comfortable with the fact that square roots have that invisible 2 for their index. So here, if we look at this, I know you guys would just automatically say the square root of 16, right? You look at that, you know it. Square roots are super, super common. So here our index is that invisible 2, okay? We don't see it, but it is in a sense there, okay? It's just invisible. We don't write the 2 in for the index, but if I said to you, what's the index of this expression, you would need to say 2, okay? The radicand is, of course, 16. 16 is what's underneath my radical. The radical is just the symbol. So it's like we have that invisible 2 there. This and this are exactly the same. They are equivalent. If it helps you, you can write in the 2. And as we move forward in this unit, it might be helpful for you to do that. And you'll see why as we move forward with this. So I hope that you found this brief introduction. Oh, and of course, excuse me, I forgot one thing. In English, we would say the square root of 16. That's this expression. Both of these, in fact, we could say the square root of 16. That's how we would read it. So I hope you found this introduction helpful, and I hope it will help you as you move along in this chapter and in this unit. Okay? See you guys soon.